Hello and welcome to today's class, that is Unit 3, Article 3 from Unit 2, and it is dedicated to metallic bonds, very interesting bonds. And as the name tells, these bonds appear in case of metals or metallic crystals. So, in all, the whole class is dedicated or concentrated upon three different points from the metallic bonds, that is metallic bond and metallic crystals, then formation of metallic bond with an example, and we'll conclude with the properties of important properties of the metallic bonds. So, we are familiar with the covalent bond, and we have seen that covalent bond is formed due to the sharing of electrons by the neighboring atoms. But important thing is that once the electrons are shared by the neighboring atoms and bond is formed, the pair of electron that is shared by the two atoms in case of covalent bond is totally the resides in between the atoms, okay, which are sharing the pair of electrons. That means the sharing of electrons in case of covalent bond is a localized sharing, or the sharing is saturated. So it is a nature of a covalent bond, sharing of electron in a covalent bond. But in case of metallic bonds, the metallic bond is formed by sharing, but not like a covalent bond. It is a partial sharing. So metallic bond is formed by partial sharing of electrons by the neighboring atoms. What do we mean by partial sharing? Okay, the sharing is not a localized sharing. That means when two atoms came near to each other, they share electrons, but the pair of electrons they shared, the pair of electrons will not remain at all in between the two atoms, or it always does not form the bond between the two atoms, or it will not remain in between the two atoms. It is not the property of the two atoms. It fluctuates throughout the metal, and this is called as delocalized or unsaturated nature of the bond. Okay, if it is compared with the covalent bond, we can call it as a delocalized or unsaturated covalent bond. Okay, so what is metallic bond? The bond formed by partial sharing of electrons between the neighboring atoms, where sharing is not a localized one. In short, delocalized or unsaturated covalent bond is a metallic bond. Now, what exactly are the metals and how metallic bond works? It was proposed first of all by the physicist Drude. And what is Drude's proposal is that once the metal is formed, the atoms in the metal contribute electrons to the common pool of electrons, or which is also called as free electron cloud or free electron gas. That means once the solid or metallic crystal is formed, okay, the atoms fix their positions, but their electrons which they have shared partially, and due to partial sharing, the electrons which are not localized one, they are delocalized electrons. So these electrons from delocalized pair of electrons are free to move throughout the metal, and they form a common pool between the atoms, and that common pool is of free electrons, that is called as free electron cloud or free electron gas. This free electron cloud or free electron gas work as a mobile glue. Glue means the thing that bind two things together. Okay, so here the glue is mobile. Okay, that means moving glue. So free electron cloud or gas work as a mobile glue, and it bind the positive ion cores. Now atoms has lost their electrons, so they are no longer atoms, but they are positive ion cores which are fixed at their positions. So the mobile glue, the electron cloud or electron gas will work as a mobile glue, and it binds the positive ion cores by the electrostatic force of attraction. Okay, and this electrostatic force of attraction works due to positive ion of the cores and the negative charge on the free electron cloud, and in this way the bond formed is called as the metallic bond. Atoms can share a required number of electrons with their neighbors through the common pool to complete their octet. See, this sharing basically happens to complete the octets of the atoms, and in this case the common pool of electrons is continually moving throughout the array of positive ion cores, and atom can share a required number of electrons to complete required number of electrons with its neighbors to complete their octet, and for that purpose it can acquire the electrons from the common pool, that is the free electron cloud. Okay. Now, due to the free nature of electrons, or due to the free nature, the electrons can resonate between the atoms, and due to which the metallic sharing changes with time. Okay, the electrons continually resonates between the atoms, and metallic share changes with the time. So that we will see how the metallic sharing changes with the time due to resonating behavior of the electrons, that we will see in the example of metallic bond, and that example is of sodium metal. See, the electronic structure of sodium metal is somewhat like this. It has 1s, 2s, 2p and 3s, 4 different shells. 1s is completed with 2 electrons, 2s is again completed with 2 electrons, 2p is again completed with 2 electrons, but 3s has only 1 electron. It has vacancy, it has need of 1 electrons to complete. Okay. Now what happens when near to such an sodium atom which has 1 deficiency of 1 electron in its 3s atomic level? Okay, it has deficiency of 1 valence electron. Then 2 sodium atoms share the valence electrons in the 3s orbit, and an electron pair bond is formed. Okay, only the condition is that electrons must have opposite spins. In that case the bond is formed, or more chances of formation of bond are there. Okay, so it is the sharing, okay, no problem, but the interesting change will happen when the third sodium atom came near to this pair of atoms. Okay, now what happens? Since the octet, the valence shell, 3s shell of both the sodium atoms are completed here. Okay, this sodium atom and this sodium atom, their valence shell is completed since they shared a pair of electrons. Okay, so there is no possibility that another electron will enter in the same shell, because it will violate the Pauli's exclusion principle. Okay, now what happens? Okay, though it cannot, the third sodium atom cannot form bond with the 2 atoms simultaneously. For that purpose, what happens is here, the criteria is that since the sharing is completed here and there is no place for this third sodium atom to share electron here, okay, because 3s shell is filled of both the atoms. What happens is that 1 electron from 3s shell move to 3p shell. Okay, and it is possible because the energy difference between 3s and 3p shell is very small. Okay, so what happens now? The electron of the third atom is in 3p shell, and it can form now the bond with any one of these sodium atoms without violating the Pauli's exclusion principle, because in its 3p state it can accommodate 6 electrons. Okay, and in this way the third atom form the bond with any one of these 2 atoms. Okay, important is to note that the third atom cannot form bond with the 2 atoms simultaneously. Okay, important thing is that. So, okay, so it means it can form one half of the electron pair bond with each of the other two bonds. Okay, and in this way its bond is completed. Okay. Now, however, structure of sodium atom is BCC, or sodium metal is BCC, body centered cubic. That is, each Na atom forms 1/8 of electron pair bond with each of its 8 neighbors. Okay, so we are familiar with BCC structure where the coordination number is 8. That means one sodium atom has 8 nearest sodium atoms. That means one sodium atom can form bond with 8 sodium atoms, and in this way not 1.5 but 1/8 of the electron pair bond is formed by a single sodium atom with all its 8 neighbors. That means there is the pair of electron is always not localized or not fixed between the 8 atoms, but it resonates, it moves between the 8 pairs. Okay, at a time only one pair of electron is there and other are the half pairs. So that is the important thing. So what we call it as electron pair resonates between the 8 pairs and it completes the 8 bonds. Okay, one by one, and hence it is not a saturated one, but it is an unsaturated or incomplete covalent bond. Okay, metallic bond is unsaturated or incomplete covalent bond, since the electron pair resonates between the number of atoms. The valence electrons in this way are delocalized and move freely, since the pair of electron that bind the atoms together is not fixed one and it rotates between the number of atoms, as in the case of sodium between the 8 atoms. The electrons are not localized one, they are delocalized and free to move in the crystal, and they are called as free electrons and they give rise to a free electron gas. Okay. Now, due to such delocalized nature of valence electron, the metallic bond is much less directional than the covalent bond. We are familiar with the directional property of the covalent bond, particularly the covalent bond in the diamond. Okay, and it is because the pair of electrons shared by the two atoms in the covalent bond is fixed at its position. Okay, so therefore it is strictly directional bond. Okay, but it is the metallic bond in which sharing is partial and shared electrons are not fixed ones. They are delocalized, they are not localized down, they are delocalized type of electrons, and hence metallic bonding is not a directional one. It is much less directional than the covalent bond. Okay, since it is a less directional bond, the metals prefer to form close packed structure, that is hexagonal close packed structure or face centered cubic structure. Okay. Only the alkali metals are exceptional cases, okay, in which as we have seen the example of sodium, where the structure is BCC and BCC is a loose packed structure. Okay. Why? How it can be explained? It can be simply attributed to low melting points. Okay. If we consider the melting points of sodium, melting point of sodium and other alkali metals, they are far near or smaller than the room temperature. At room temperature, they start vaporizing or liquefying. Okay, so their melting points are very low, and the atoms of the solid vibrate with large amplitude near the melting point. So this is the important. And since they are vibrating with large amplitudes, the loose packed structure is produced in case of alkali metals. So in case of alkali metals, due to their low melting points, atoms are vibrating with large amplitudes and they possess loose packed structure. While another exceptional case is the iron. In case of iron, though it is a metal, it does not prefer the close packed structure, it prefers the BCC structure. Okay, and other transition metals like iron also possess the BCC structure, which is loose packed one. It is because their partial covalent character, as we have studied here. Okay, in these metals, electrons are present in the d orbitals, which participate in the formation of metallic bond, and d orbitals are strictly directional bonds. The d orbitals form directional bonds, and tendency of these directional bonds is to produce close packed structure, to produce the loose packed structures. So therefore close packed structure is inhibited in case of the transition metals like ions due to the d orbitals taking part in the formation of metallic bond. Okay, let us have a few properties of these metallic bonds. The metallic bonds, as we have seen here, due to their free electron nature, they are weaker than ionic and covalent bond. We have seen that the energy, binding energy per bond is more than 5 electron volt in case of covalent and ionic bond. But in case of metallic bonds, binding energy is 1 to 5 electron volt per bond. So they are weaker than ionic and covalent bond. The melting and boiling points of the metallic solids are lower than ionic and covalent bond. Again, it can be understood from the less binding energy. Important property that is acquired by the metals possessing metallic bonds is they have high ductility and malleability. Okay, so it is due to the free electron nature of electrons, and that we will see in the next coming unit, that is fourth unit in detail. But remember here that high ductility and malleability are the properties of metallic bonds. Another important thing is that since they have huge number of free electrons, okay, these free electrons helps in conduction of electricity and heat, okay, and therefore the metallic metals or metallic crystals possess high electrical and thermal conductivities. And another one is that they have high reflection and absorption coefficients. Okay, due to which we observe the metallic luster on the metallic bonds, and again it is due to free nature of electrons. With this we conclude the metallic bond here. Thank you very much.